I'm going to take you through this video tutorial of wiring a microphone and performing a DFT in LabVIEW 2009. This video tutorial is made for ME 4031 students here at the University of Minnesota. Prerequisites for this video are a simple data acquisition video tutorial, LabVIEW 2009 installed on your computer, a USB 6008 or similar data acquisition device, and the microphone hardware. First we're going to build the microphone circuit, then we're going to acquire the voltage data, then we're going to perform a DFT to look at the frequencies inside of it. The microphone circuit is taken from the spec sheet from the CUI 6554 microphone. The microphone has two terminals on the back side. The terminal 2 is wired with solder tabs to the case of the microphone. These terminals were labeled incorrectly in the spec sheet. In addition, we'll need a 1 kilo ohm resistor and a 1 microfarad capacitor to complete the microphone circuit. When the microphone circuit is wired together, it'll look like this. Terminal 2 with the solder tabs is connected to black, which is connected to ground. Terminal 1 is connected to the 1 kilo ohm resistor, which goes to plus 5 volts, and the 1 microfarad capacitor, which is the voltage we're going to measure. When it's wired up to the 6008, it'll look like this. Black goes to ground, red goes to plus 5 volts, and blue is going to go to AI6, which we choose to measure the voltages. The example we're going to use here is we're going to measure DTMF tones, which are touch tones that are played when you push a keypad on a telephone. When you push a 1, it's a combination of two tones, a 697 tone and a 1209 hertz tone. We're going to use the keypad button press of 1 for this example. We'll go to LabVIEW, start with a blank VI. We're going to take in voltage data from the 6008, so we're going to go to Express, Input, and we're going to use the DAQ Assistant. We're going to acquire signals that are voltages. We're going to take it from the 6008. We know it's pin AI6 because that's where we wired it. Now when we go, we're going to change the samples to 800 samples at a sample rate of 8,000 samples per second. So it's going to take about 100 milliseconds to get all the data. We click OK. First thing we need to do when using Express block is to convert it from dynamic data to something useful. And we're going to do that by right-clicking, going to SigmaNIP palette, and going from dynamic data. We need to tell LabVIEW what sort of data it is we're going to look at. We could choose a 1D array of scalars, but that'll only give us the voltage data that was measured. If we go down here and choose single waveform, that's going to give us all the voltage data plus the time data that corresponds to it. So we'll click OK. We wire that together. We add a waveform graph to the front panel, so we can just look at this data right away. Wire the waveform to the waveform graph, run it. We see the output from the microphone. The DC offset centered about 1.4 volts DC offset. We have some fluctuations there. I'll add some noise with my voice. Ooh. We can see all the voltage fluctuations due to my voice. It took about 0.1 seconds or 100 milliseconds to take all the data. Well, this isn't very interesting. What we actually want is the frequency components inside of here. In order to find that, we need to do an FFT of it. So we right-click, go to Signal Processing, Waveform Measure, and go to FFT Power Spec. You see in FFT it takes in a bundle called Time Signal. This is the waveform. It has both time and voltage data on it, and outputs the power spectrum, which is going to be frequency and power, but they're both bundles. So first we wire this guy over to here. We can have a look and see what's inside of this bundle by going to Waveform Palette, get Waveform Components, wire it together. And you'll see there's three things inside of it. A T0, which is the initial time the data started happening, DT, which is the distance between each of the discrete time samples, and Y, which is the actual voltage data that occurred at each of those time samples. Well, we have the same thing going on as the output this power spectrum. I'm going to right-click, go to Cluster Class, Unbundle, connect it to this power spectrum here. And you can see we have similar three things inside of it. We have some initial frequency, some frequency resolution, and the magnitude and array of all those values. I'm going to create an indicator now for each of these values so we can look at them on the front panel. The first two are just going to be scalars or single values, and the second is going to be an array of all of the it's going to be an array of all of the voltage, the powers for each of the frequencies. You see this is an array. I'm going to drag it down so we can just have a look inside of it later. Now because these are built the same way, this is time and this is frequency data, it means we can use this waveform graph to look at the FFT too. So I can just drag him down here, connect him to this power spectrum, do a Control B to clean up the broken wires, and run it. Now we have an FFT happening over here. Now you see we have a DC offset is our largest value, and it with a value of 2 there. Now, because this isn't very interesting, the voltages, the frequencies we want are down over here, and they're a very small amplitude. So I'm going to resize this to 5 times 10 to the negative 5th, and I'm going to undo auto scaling. Now, when I do an FFT, well, let's see, nothing showed up there. I can hum into it. Ooh, you see my voice, or I can play this DTMF tone and acquire that data. Now you see the DTMF tone has 2 frequency components in it. That's 700 Hertz, remember 700 Hertz, and a 1200 Hertz tone. Well, there we go. Now you have an FFT of your data, and you could tell what DTMF tone it is just by looking at this and guessing. But you might need to go further than that. You might need to know exactly what frequency this maximum value occurs at. Well, in that case, you need to drill down inside these components that are inside of the cluster. And you need to search inside of this magnitude array here and find the maximum value that occurs inside of it. Now we know, first of all, the maximum value is going to occur at 0 Hertz, but let's search anyway. Go to array, use the min and max function. This takes an array, it gives you the max value and the index inside that array that the max value occurs at. We connect them to the array. We output, create an indicator to show the maximum index it occurs at. We run it over here. You see the maximum index is 0, which is what we expected because this is the maximum value. All the other frequency components are really small. This first value corresponds to a frequency of 0 because the frequency increment is 10. The second value is then a frequency of 10 Hertz. This third value is a frequency of 20 Hertz. This fourth value is a frequency of 30 Hertz, and so on. So if we find the largest value inside of here, we can tell what frequency it also occurs at. But first we need to null out these first 2 values here and make them 0. We can do that by going to the array panel, going replace subset. That's going to take an array. We're going to tell what index and what value we want to replace there. So we say we take this array. At an index of 0, we want to input a value of 0. And because we have some residual in the second value here, we're going to copy it and we're going to just do it again. Control-C, Control-V. And now at an index of 1, we're going to also replace that with a 0. And then I'm going to create an indicator to look at the output here. I'm going to expand it so we can look inside of it. I'm going to run it. And this new array now is exactly this array up here, except these first 2 values are now 0. So when we do this min-max, when we find the min-max now of this array, we're going to find the min-max of these values. So we find the maximum value occurs at an index of 237. Because df is 10, that means it's a maximum value of 2,370 Hertz. To make it a little more transparent, we can just multiply over here the maximum index times our df. We can then create and make an indicator again on the front panel. So this is the maximum value excluding the DC offset that's occurring in the signal. So if I play a DTMF tone again, collect the data, we see then it's saying the maximum value occurs at 700, which is correct, and the second value is around 1200. It's a little smaller, so to find that we'd have to null out these values and then research again to find the smaller value here. Now because df is 10 Hertz, this comes from the sample frequency and the number of samples that we took in the DAQ assistant here. Remember, we sampled at 8,000 Hertz. Now with the Nyquist criterion, it says this value can only be 4,000. We can only find a value that's half of the sample rate. And also we took 800 data points, which means the FFT is going to have 400 data points. So we have 400 data points spread out between 0 and 4,000 Hertz. So the increment between each of the data points is 10 Hertz, df of 10. To reduce df of 10, we can either decrease the maximum sample frequency, or we can increase the number of data points. So our value here is 700 plus or minus 5 Hertz. So to find this more accurately, you'd need to decrease this df here. Other resources available to you: the CUI datasheet available online. DTMF is from Wikipedia, and DigiKey Electronics has all their spec sheets available for you online. Good luck!